Hi, um, good morning or good afternoon or good evening, fellow classmates and also lecturers who are watching this. So my name is Ming, and today we have my team, which me is Sherlena, and we'll be going through more about our analyzed malware, which is LuckyCat. So for today's contents, we'll be going through some basic information about the malware, the lab setup, followed by the tools used for analysis and what kind of analysis methods we have used to analyze LuckyCat, after which we'll be going through our conclusions and reflections of this project. So now on to some basic information about LuckyCat. As though its name says that it's a lucky cat, it has not made its victims feel very lucky. So LuckyCat is actually an advanced persistent threat that was first discovered by researchers in 2012. And since then, people have actually realized that this malware has been active since 2009, as early as 2009. And then after that, it is also has been attributed for several high-profile cyber attacks, including the 2011 RSA breach and also the 2013 attack on New York Times. So the group behind this malware is actually known for its use of sophisticated zero-day attacks and tactics to compromise target networks and steal sensitive information through the use of LuckyCat. Yeah. So right now, I'll pass over the time to Sherlena, who will be sharing more about the lab setup that was used to examine LuckyCat.
So for the lab setup, firstly, our team was using both the Windows 10 and Windows 11 Professional on our local hosts, on our local machines. So for both of our laptops, it was running the virtual machine workstation 16 Pro, which is VMware, and within this VMware, we hosted the Windows 10 Professional, and we installed in the FlareVM tools. So for the host machine, we made use of one Windows 11 Pro machine running on the following processor with 32 GB of memory and the system was a 64-bit operating system. So the other machine that we were using was running a Windows 10 Pro and the following was the processor, and it was running a 16 gig of memories. So next, for the virtual machine, the reason why we use the virtual machine was to ensure that there was isolation between our host machine as well as the machine of where we are running our virtual machine on. So this will help ensure that our device will not be infected with the LuckyCat malware. So for the operating system of the virtual machine, we use the Windows 10 Pro, and we use around 8 GB of memory which is running the 64-bit operating system. So we installed the FlareVM tools, which is compatible with Windows 10 and up virtual machines. So FlareVM is an open source tool which compiles the various software installation scripts for the various tools required by malware analysts. So these scripts will actually aid in the quicker installation for the various tools that are usually used within the malware analysis process. So next, on to our network configuration. For the network configuration of the virtual machine, we use the host only settings. So there are different configurations that we are able to configure, being the bridge, net, host only, as well as the LAN segment. The host only network configuration is used as it is only connected within a private network with the host, which means that the malware will not be able to connect to the internet or will not be able to use another IP address connected to our same internet, ensuring that both our host machine as well as other machines within the network will not get compromised by this malware. So for the tools used, which are web-based, we have VirusTotal, CyberChef, and Text Comparer. So VirusTotal is a tool which allows the users to upload and search for files, URLs, IP addresses, as well as file hashes. It makes use of multiple antivirus engines, which is able to detect if the file or a URL is malicious. So for CyberChef consists of various encryption and data extraction methods. So using this tool, malware analysts are able to detect the algorithms if they are unable to detect. So using their magic tool, and we are also able to make sense of the information that we actually found, which are encrypted by the malware. So for text comparer, the text comparer allows the user to compare the changes between large bodies of text. So in this case, we'll be using it for our string analysis, as string analysis consists of a long list of strings. If we use just a plain iPower, we may miss out some essential changes made by the malware. As such, the text comparer, which helps to highlight the information which is different from the file, will be useful. Next, passing on to Ming about the tools being used for the basic static analysis.
Thank you, Sherlena. So back onto the tools that we use for basic static analysis, which is actually one of the 4 methods that we use to analyze LuckyCat in this report. So basic static analysis is an analysis method that focuses on using automated tools to understand and also have a starting point of understanding and comprehending what LuckyCat can actually do and its functionality. So let's get into it. So for our first tool, right, we've actually have WinMD5. So WinMD5 is able to calculate the file's hash and is also commonly used to check if any files created by the malware is actually the same as malware. So this point is quite interesting because certain malwares out there, or actually a common trait of some malwares out in the wild, is that they like to duplicate their own malware and rename it as another file on the system. So by using WinMD5, we are able to uncover whether a certain file that's stored on the system is similar to the malware, which is true using the hashing algorithm that WinMD5 provides. So for our next tool, we have PEiD. So what PEiD does is that it can identify the packer of the executable file, and it actually uses a database of signatures to recognize which packer an executable has. So the third function of PEiD is that it also is able to check whether the file is packed or not. So how it does that is that PEiD has 3 different types of scan: normal scan, deep scan, and hardcore scan, which is able to display further details on the malware and also display the raw and virtual size of each section of the portable executable, so that we are able to see whether the executable is indeed packed or just not packed. Yeah. So the next tool that we have, right, is PEview. So PEview actually shows the date and time stamp of when the malware was created, and this actually can be used to create a timeline of events with the other section headers that may contain also the time and date stamp. So this will give you a rough idea of when the malware was created and when the malware author actually wrote out or compiled each and every section of the malware. So next tool that we have is Dependency Walker. So Dependency Walker, what it does is that it shows the imports and exports of the DLL files used by the malware. So what it does is that it helps us to identify some possible functionalities of the malware, perhaps through the identifying common import or export functions that are able to be found on the Microsoft documentation online. Yeah. So for our last tool for basic static analysis, it will be BinText. So BinText, what it does is that it extracts strings from the malware and displays them out for the user to see. So this is a very good way to highlight what strings are important out from the malware and uncover some host or network-based indicators. So what this means is that essentially, BinText can find certain keywords that may appear within the malware. For example, perhaps a URL link, or perhaps showing some changes to the registry keys. So it actually does give us a deeper understanding of what the malware is really truly capable of. And it is a pretty good start in giving certain context in understanding what LuckyCat or whatever malware that you are analyzing, what its functionalities and capabilities are. So now I'll pass the time to Sherlena. She'll be talking more about the basic dynamic analysis tools.
So for the process of the basic dynamic analysis, the following tools were used: Process Explorer, Process Monitor, RegShot, ApateDNS, as well as NetCat. So Process Explorer helps to provide the insights on the active and running processes, the various handles, and the data link library files which are running within a certain application. It is also able to view the strings in both the image and memory to view whether there is any changes within the strings that are loaded into the system. So another thing that our Process Explorer is capable of doing is to create and kill processors, and they are able to verify for a legitimate process if it is digitally signed by Microsoft. So next, for Process Monitor, it monitors the changes made by the various processors. It has preset filter values to ensure that you are able to find what are the specific executable that you are trying to find to view the operations for. So allows you to view the registry operation, file operations, the locations of the operation where it's being performed, and as well as the details of the operation performed. And for RegShot, it helps to capture all the configurations set within a specific directory. So it helps to compare the changes made between the two shots. The first shot, which is usually taken before the malware is executed, and the second shot after the malware has been executed. It allows the users to actually output the logs in either plain text form or a HTML document. So this will help the malware analyst view the registry operations that has been done within that specific directory that they have selected. For ApateDNS helps to monitor the DNS connections made out of the systems. So it captures the domains that are actually queried, and based on this information, the malware analyst is able to learn more about which domains are being requested for, and which domains the information may be sent out to. So the ApateDNS allows the users to also configure the DNS reply IP address, and usually the options that is set by malware analyst will be the 127.0.0.1, which is the loopback address for the system. This will allow the analyst to actually view the operations of they'll be able to view the network operations made outbounds from the machine that they are running the malware on. Lastly, for NetCat, NetCat is able to monitor the connections both inbound and outbound, and is able to capture the data sent. So we can learn the information being sent over from this, as well as the information that is actually being accessed by the malware. So using the NetCat command, we can listen. We'll usually listen in for the incoming connection, and we will specify the verbose output as well as the port that we are connecting towards.
So now onto the tools used for more advanced analysis. So firstly, for advanced static analysis, which is the method of analysis by analyzing the source code without running the portable executable, so that you can understand the code and what the functionalities and what the executable is meant to do. So the first tool that was used was IDA. So as you can see on the slide, it's IDA. It's stated that it's IDA Pro, but there's actually a error on the slides. It's IDA free, but despite this, we're still using IDA, so it's still pretty much the same, just with limited functionalities. So firstly, about IDA, it is a disassembler and a debugger. So, but unfortunately, as we are doing static analysis, the debugger functions will not be touched upon during this report, and also during this exploration. And secondly, one feature that I extremely love about IDA is that it has this graphing feature that is able to visualize how the code blocks and also how the program flow of the portable executable is run. And another good thing about IDA is that it enables the users to view the strings and also the hex of the malware code. So if you do need a change between several of these different functions, it's freely found on IDA. So another tool that was used for static analysis was also Cutter. So Cutter is a disassembler and a decompiler. So although it's somewhat similar to IDA, what Cutter was primarily used for in this project was its decompiler features, as it is able to convert and display code so that users can see code assembly code that is decompiled into more human readable or higher level language code, so that it's easier for people to understand what the code is trying to do or carry out.
Okay, so for the X32DBG, this X32DBG is built for a 32-bit system. It's mainly used to analyze the code as well as a running of the debugger. So the X64DBG is also available for the 64-bit systems, but as we are analyzing a 32-bit malware, the X32DBG tool is used. So the X32DBG tool is able to decompile files into assembly code, perform debugging, viewing of the graph of the malware, viewing of the registry values, as well as the stack. So this will all be used and analyzed during the process of conducting the advanced dynamic analysis. So next on to our analysis, we'll have the basic analysis of the basic static analysis, followed by the basic dynamic analysis, advanced analysis for the advanced static analysis, as well as the advanced dynamic analysis.
All right. So for basic static analysis, as previously mentioned, what it does is that it helps malware analysts to gain the initial idea and concept of what a certain malware's functions and capabilities are. So the good thing about basic static analysis is that it does not require the analyst to have strong technical knowledge on how to use the tools. However, there needs to be some very basic knowledge in terms of interpreting the results of the tools, which is easy for a lot of people to do. So tools that were used in the basic static analysis segment of this project was BinText, Dependency Walker, WinMD5, PEview, and PEiD, which was also previously mentioned. And all these tools actually assist the analyst in getting more information about the executable. Hi everyone, so today we'll be going through the basic static analysis for the malware LuckyCat. So basic static analysis is actually one of the 4 analysis methods that can be used to investigate a malware. However, basic static analysis is the analysis technique that actually focuses on using automated tools to analyze the malware source code and also to see what the malware has in store. And these automated tools actually give a pretty good starting point for understanding the functionalities and characteristics of a malware. So for basic static analysis, this time we'll be using WinMD5, PEiD, PEview, Dependency Walker, and BinText. However, before we start basic static analysis, I'd like to do one thing that's extremely important and vital step before any sort of analysis should be done, which is malware fingerprinting. So what this malware fingerprinting does is actually to identify and classify a malware based on its specific characteristics or attributes to, let's say, a malware sample. So actually, although there are many methods also in malware fingerprinting, the method that was used in this time's analysis is signature-based fingerprinting. So this method involves comparing the hash of a malware to a database of known malware signatures to identify the specific type of malware the malware sample that we are testing on is. So in this case, today we'll be testing on LuckyCat, and let's get into it. So to perform malware fingerprinting, first we open up our VM. So this time it's FlareVM. And as you can see here, for convenience, I've also loaded the LuckyCat a folder here, which includes, double click on this. You see that it includes the application over here. Yep. So now, firstly, I will be going into the first tool that we'll be using today, which is under PE, and we'll be grabbing apologies, not PE. We'll need to go under utilities to look for WinMD5. So as previously mentioned before, WinMD5 is a tool that is used to uncover the hash of any sort of file. So today we'll be getting the signature or also the hash of the LuckyCat malware. So here I drag the LuckyCat malware into here, and we can see that WinMD5 immediately shows us a hash of the file. So hash starts with 9F9723, and this hash will normally in malware fingerprinting, what we'll do is we'll copy this hash and we'll place it into another open source online tool called VirusTotal, which contains a signature a database of signatures of many malwares and also a lot of executables. So then we'll use this hash and compare to see what sort of malware this is. So for convenience sake, I've also loaded VirusTotal and added in the hash correctly. So over here we can see that actually the score on VirusTotal is 52 out of 71. So it means that 52 out of the 71 malware scanners have actually detected that this that files with this same hash that we've uncovered in WinMD5 actually is dangerous. So you can see here the security vendors have 52 security vendors have picked up that is likely a Trojan or password stealer, or it is generally just malicious and has malware. So that's it for the first page of VirusTotal. Perhaps if we look under the details, we can find out more. So details, it shows more basic properties like what's the MD5 hash of this, which we can see over here. It's pretty much the same, 9F9 at the start and 8BL at the end. And for SHA-1, it is in this, and in SHA-256, this is the hash. So it can be seen in the history over here that it says the creation time of this malware file actually was in 2020 and it's first seen in the wild in 2019. And several other names of the same malware is Credentials.dll, Win32.LuckyCat.exe, and several more file names. I think this one is the one that is being used in our folder here. Yep, so quite similar. So 8E9, E89 over here, and then goes on with a bunch of numbers. Yep. So it's also good to know that more information is provided on VirusTotal, and it's a very good resource. And as you can see over here under the Relations tab, it seems that several URLs are also picked up on, and also connected IP addresses. However, what is most interesting is that you can see here in the execution parent section, it seems that quite a few virus scanners have actually detected that the execution parent of LuckyCat is a Office Open XML slideshow. So what this means is that in a lot of cases, this LuckyCat malware is actually found within this Office Open XML slideshow, which is also a longer form for Office slideshows. So as you can see here, you can see that actually most of the time LuckyCat is transported around using in the form of a Office slideshow and transmitted around using this file. Yep. So with that, we've completed a simple malware fingerprinting with WinMD5 and also VirusTotal. So now we'll be moving on to the next tool. So the next tool we'll be using is PEiD. Here you see PEiD has been opened. Let's close WinMD5 for now. So as you can see here, PEiD over here is currently empty. So we'll be going into the file folder system and we'll be dragging out the malware into PEiD. So as you can see for PEiD, it started to load and you can see that the EP section here, you can see the subsystem and also most importantly, the packer that was used to pack the malware. So over here you can see Borland Delphi. And if we are still skeptical whether this truly is the packer or the compiler, can click on this arrow here and can perform a hardcore scan. So hardcore scan, what it does is that it runs a more aggressive scan on the portable executable, and as you can see, there's no change in the results. So it's pretty much confirmed that this malware is using Borland Delphi as its hacker. So back again, if we do like a quick search on, let's say any sort of search engine to search on what Borland Delphi is, it's actually a GUI IDE, and it is released for Windows. So as you can see, it's a pretty legitimate packer. So therefore, we can tell that this is one of the signs that this portable executable is not a malware. So more ways on how to find whether the portable executable is a malware or not is to look at its EP section. So over here at the EP section, we see the .text. And if we click on the arrow at the side, it will show us the section view, showing us the real size and the virtual size. So what this means is actually real size or actually raw size. Apologies, raw size denotes the size of the malware when it's stored on the disk, while virtual size refers to the size of the malware when it's stored on the memory. So usually when raw size and virtual size are somewhat similar, it means that it is not packed. However, if let's say the raw size is significantly more than the virtual size, we can tell that the malware is actually unpacked. And in cases where the virtual size is larger than the real size, then we can tell that a malware is actually packed. So why is this so? Is because packed malware compresses its code to a smaller raw size to evade detection most times. So if let's say the virtual size is more than the real size, it means that the malware is packed. So from PEiD, we have uncovered more details of the LuckyCat malware. Firstly, it's of its packer, which is Borland Delphi, and we've also uncovered the fact that the malware is unpacked due to this its raw size being larger than the virtual size in most of its sections. Yeah. Alright. Moving on to the next tool. Next tool that we have in mind is PEview. So immediately after you open PEview, you are prompted to load in the file that you would like to see and display in PEview. So I select the LuckyCat one on the desktop and the application. So you can see a hex display of what the malware is supposed to be like is seen, and you can see the MZ at the side, which represents that it's a portable executable. So if you go under the image NT headers and expand this out to the image file header, you can see one very important detail that PEview is usually used for to view, which is the time date stamp. So over here it says that this what this time date stamp means is that on 2020, on 7th month and the 9th day at about on a Thursday, which around perhaps 1 a.m. UTC time, this malware was actually created, and it was actually packed. So that gives a very important time in terms of when a timeline is created on understanding what the malware or how the malware has been created. So for example, in the other sections, for example, as you can see here in other sections, there are no like there are no values mentioning on the time date stamp. However, if there were a section, there was like a description or any sort of variable that talks about the time date stamp, then you can piece them all together for each section and also figure out which section was created when this entire malware was created by the malware authors. Yeah. So in PEview, we've only gained one important new knowledge on the malware, which is that it is on this date, it is actually a important date as it is the date when it was actually LuckyCat was compiled. Yeah. All right. So after PEview, we'll be using this next tool that is extremely useful called Dependency Walker. So as you can see, I'm starting up Dependency Walker. Just let it run. So in Dependency Walker, I go to the desktop and I run Win32 LuckyCat, the application ended. So Dependency Walker is now opening the file. So what Dependency Walker does is that it actually it reads the malware file, and then after that it extracts out and displays out the dynamic link library files of the malware. So each dynamic link library file actually contains several two main things that we'll be looking at: imports and exports. So exports are functions that are that the dynamic link library, or also known as DLLs, actually provide. So it exports all these functions out of its own code, and then it provides these functions that it has to other DLLs to reference or to use. Oh. Seems like Dependency Walker is a bit slow today. So going back to the topic I was mentioning just now, also we'll find an import table and export table when we open up our Dependency Walker. And as previously mentioned, the export table is where all the functions that are exported out of the of each DLL, which allows other DLL to use, while the import is actually functions that are being used by the DLL by itself. Okay, so if you do receive an error over here, no worries, you can just exit out and you'll be in. So this is the interface of Dependency Walker. You can see here that there's a lot of red errors here and there. No worries. And also you can simply minimize all of these. It looks a bit scary at first, but if you're able to minimize all of these are all just simply sub DLLs that are under the one main big DLL. Okay, so now we have packed this, cleaned this up here. So you can see that there are actually 6 main DLLs for LuckyCat's malware. So kernel 32, user 32, advep 32, ole 32, SHL WAPI.dll, and WS232DLL. So before we dive out and get our hands dirty in each of the DLLs, firstly, I just want to point you to this export function here, get object count. So what this means is actually to call upon the exe or to run it, you'll need to actually use this function, call upon this function, so that the rest of the DLLs are also mentioned and called upon. So we'll see this more in the basic dynamic analysis, where this function is used to run the malware, and also further later on in the advanced static analysis, where you can see the function in the IDA3. Okay, without further ado, let's dive into the first kernel, the first DLL, kernel 32. So as you can see, we'll look on the import table here. So there's several functions here of creating event, creating a file, creating processes, deleting a file, find first file exa, and find first file w. So there's several file related functions over here. So we can start to deduce that this malware actually has file manipulation and also file viewing capabilities. And if you scroll down a bit more on the import table, it also seems that there's a get computer name and get computer name w here. So these two seems to be also collecting information on the computer in respects to its computer name. So this might be a bit interesting. As we scroll down more, you can see that there's also more commands that and functions that are used to perhaps suggest that LuckyCat is able to collect information on the victim's computer. So over here you can see get this free space. So it seems like this function will be getting the amount of free space left on the disk along with the drive type. And as you can see, there's more file related functions. And as we scroll through, we do see quite a few functions here and there. Most of them are rather still quite generic in terms of its usage. It mostly helps the DLLs to run. Perhaps another interesting function of note is sleep. So sleep here is actually a function that is commonly used to pause a certain thread or process when it runs. So the reason why this is actually so important in terms of a malware's context is that sleep is used so that malwares actually stop their processes. And when they stop their processes, what it does is that it makes it so as if the malware is seemingly not being run on the victim's computer. And what this does is that malware detectors or any sort of like anti-malware scanners that may exist on the victim's computer will not be able to detect the malware. So that's why sleep is usually quite common function when in terms of a malware. Yeah. So you can scroll down and see that we reached the end of the import table with the last few being right write file and write to console. So perhaps we might see some command line functions in the future. So it's also suggesting that LuckyCat writes to the command line to perhaps execute certain commands. And at the bottom, we see some string length functions and string copy functions. So it seems that there might also be some copying and finding out of length of the strings. So if we scroll down on the export table of kernel 32 DLL, it's mostly quite messy and it's referencing mostly all the, you can see some sub DLLs that are used and copy file, which throws back relates back to the suggestion that LuckyCat has file manipulation functionalities, and also see more file related functionalities. And that's pretty much it for kernel 32. There's actually quite a lot to look through here, but not all of them are actually important. So I think the most important ones have already been highlighted from the import table. So let's move on to user 32 DLL, which is the second DLL. So over here we have a printf, which essentially means to print, and also a character lower and character upper on the import table, and that's about it. So if we look down on the export table though, you can see quite a lot of normal Windows functions which are used usually to like support the processes in running or Windows in general to run. So not really too much here and there. So it seems that through the user 32 DLL, it might also possibly suggest that the LuckyCat might be getting gaining more information of the victim or target's computers, like settings and all, or just general information. So you see here there's a get window, desktop window. So there seems that LuckyCat might possibly also have some features that collects the data of the victim's computer, and it also like so you can see here also get keyboard state and get keyboard type also suggests that LuckyCat might have some keylogger functionalities too, and it seems that most of the export functions here can possibly be used by LuckyCat to further understand and also to further help the attacker to know what sort of computer or device the victim device is. Ah, I also have seemed to missed out a function just now. So this one here, get async key state. Get async key state is actually a function that is commonly used to pull the state of a specific keyboard key that's being pressed. So this actually also contributes further that perhaps LuckyCat has key logging features and characteristics. So that's it for this section on the export table. However, if we scroll down to around where the eyes are, you can see here that there's inject keyboard input and inject mouse input and even pointer input. So as you can see here, it's also suggesting that LuckyCat may have certain functionalities that may help the malware attacker to perhaps inject certain keyboard inputs or mouse input to control the computer. So I think that is quite an important point of that's from user32.dll. So the third DLL at webby32.dll, so you can see here straight off the bat from the import table that there's a lot of registry related functions. So like registry close key, create key, open key, query value, and set value. So there's quite a lot of keys here that are registry keys that are possibly being edited for. So this actually suggests that LuckyCat is actually a malware that also touches on the registry keys and edits them. So now we'll move on to the export section of adverb32. So you can see here, just a quick glance that under the A section that there's like audit lookups and queries and also audit set global. So seems like LuckyCat is also able to possibly have audit looking and lookup and query and also setting of global settings and policies within the victim's machine. And apart from that, you can also see under, if we scroll down even more, that you can see here that it's also seeing, we see a lot of crypt, which also may be referring to cryptography. So as you can see here, there's crypt decrypt, there's also crypt encrypt. So perhaps what LuckyCat may have or may have a functionality that encrypts or decrypts maybe perhaps files or registry keys so that they are unable to be seen or edited. So it is quite an interesting feature. So another interesting one is actually CVE event write function. So what this function does is it actually pushes out a Windows log when an attempted security vulnerability exploit has actually been found within the victim's device. So with this with this function here, perhaps what LuckyCat may be doing is that it suppresses this function. So every time the CVE event write detects that the LuckyCat malware is being run on the victim's computer, it could possibly LuckyCat could possibly be suppressing the output of this function on purpose, and so that it can maintain persistence. This is the same as previously we saw the sleep function too. The sleep function is also used to evade detection and also evade from alerting authorized personnel to mitigate these issues. Yeah. So these functions are just to simply maintain the persistence on the victim's computer. However, it's a quite interesting find too, as it shows the defensive practices that are possibly taken by the malware so as to maintain persistence on the victim's computer or device. So next up, we go into the OLE32 DLL. So the first thing we see in the import table is co-create GUID, and we actually will go further into that with this in the advanced static analysis, as this function is talking about creating a global unique identifier so that globally unique identifier so that it's easy for so that it's easily referenced once this GUID is created in the future, and it's also easily identifiable. So now let's explore the export table of OLE32. You can see several stuff. So once we get down to around the O section, we can see OLE create from link, create link to file. These are all actually, with all these functions here, it means that and all these function actually like permits the creation of embedded files or objects through the clipboard. So what it does is that it allows duplication of data from one file to another. So and it's also a possible tool that the malware LuckyCat is actually using, as sometimes a lot of commonly malwares like to common behavior is like they like to copy the original malicious code from a remote network location onto the local computer. So all these sort of behaviors of copying the malicious code, perhaps the source code from the actual perhaps is hidden in a document, so or embedded within a document. So this malicious code is then copied and run within the victim or target's computer, which causes the victim's computer to be compromised. So that's one thing interesting about the OLE32 DLL. So on the second last DLL, we see several string comparisons and copying of strings here in the import table. And if, let's say, we look more on the export table, there are quite a few. You can see here it's not a typical DLL. As you can see previously, we see a lot of function names. However, in this DLL, there's a lot of NA function names, like not applicable function names. However, we can see their entry point. So it's definitely refreshing. You can see here that once again we see creation of files from the kernel 32 DLL that we previously saw, and we also see like things like the printf from the user 32 and many more over here. Oh, so just nice. The glitch has allowed us to scroll down further onto the export table and actually reach the place that we're looking at. So you can see over here there's a shell 32 and then shell get file info, and we can get a shell 32 drag query file. And if you scroll down further, you can see further shell 32. So what this does is referencing to the command prompt or the command line that is within the Windows, and it's actually referring to this, the command prompt. So the command prompt on any sort of Windows machine can actually be used to run the malware, or it can be actually used to navigate into like browse directories and also look for files and folders within the file system of Windows. So it's actually quite important because the malware may possibly be using these functions so that it's able to navigate the directories of the file systems that the target computer has. So lastly, and most importantly too, also, we go into the last DLL here that says, which has actually two imports here, free address info and get address info. So these two are actually used for IP address resolution, which helps to resolve, let's say, a human readable URL to a machine or computer device readable and understandable network location that it can direct the user and connect the user to. And furthermore, over here in the export table, we can see several more functions. So WS2 actually stands for Windows Sockets 2, and what a socket does is simply to create an endpoint for a two-way for like a two-way communication over the internet to occur. So as you can see over here, this socket will set up a remote connection to the network location set specified. Yeah. So you can see here connect perhaps, and then accept function. What does is that it accepts data from the remote location. And if you scroll down more, you can see also the socket function and several free address info, get address info, which does the IP address name resolution. And that's pretty much it about the Windows socket. So as you can see from Dependency Walker, it's actually a very useful and powerful tool that we managed to uncover several possible functionalities of LuckyCat. So we'll now move on to our last tool that's used for static analysis, which is called BinText. So here we start up BinText. So it's a very small interface, so I'll try to make this a bit larger. And I will then drag the malware into BinText. So now in BinText, we can see that the LuckyCat has actually been opened and the strings have been extracted from it. So if we do a very quick scroll through, because most of these texts here are pretty much junk, and you can see that there's quite a bit of junk here and there. See the days of the week and the months, and the malware itself loading the alphabet. After that, we start to see more names, function names, like get system time as a precise file. And if you scroll down here, you can see that the DLL is then starting to connect to WS and then D. So what this might possibly suggest is that the DLL might be starting to connect to a WebSocket or a web service. So you can see that the DLL has really taken the initiative to contact a remote network location. So might be possibly contacting the remote network location to perhaps get into contact with the malware authors or the attackers. Or perhaps it might be copying a file from the remote location to copy it into the local victim computer. So now that we've scrolled down, you can see here there are more functions also. So you see firstly Credentials.dll, which if you do remember from our VirusTotal scan, it is actually a suggested other name of the file. So we know that Credentials.dll means LuckyCat Malware. So this malware is so with this string we can see that the malware is probably run, and then the first export function is then seen, the get object count, and after that we can see that there's a string len, output debug string, which are functions also here are being run, followed by the sleep function. So then there's also furthermore functions that have been seen in the analysis in Dependency Walker. Remember the registry queries and registry function related functions, and we do see the co-create GUID also here, and a lot of repeated imports and exports in here. So if we scroll past this section here, you can see more junk text. So our goal from BinText is to extract out more interesting strings here. So as you can see, we've reached a section where, once again, there's a bit more interesting information. So over here, this adverb P32, which references the DLL adverb P32 that we've seen in Dependency Walker. And these two here are also sub-DLLs that are contained in the main DLLs to help Windows to function. And then we do find a DLL that we have actually not seen within Dependency Walker previously, mscory.dll. However, a quick search online on what this DLL is actually, it states that there's an essential file for execution of managed code. So it's actually vital for Windows to run on, so that's why this DLL is here. So it's also suggested that this DLL is used to help out in the running of LuckyCat, the LuckyCat malware, or any sort of executable file that's run on Windows. And hence over here you can see more sub-DLLs that are mentioned, and a lot of trash or ununderstandable text here. So we quickly scroll past through it. And over here, we do see that towards the end of all these nonsense strings, we do see this URL look like thing here, Dalai Lama trustindia.ddns.net to port 110, and another one to port 443. So port 110 is to the POP3 protocol, which is an email transfer protocol, and 443 is for HTTPS, which is for loading websites. And lastly, over here, we see another possible IP address, 115.126.6.16, and at the port 110, which is port 3 protocol once again. Yep. So if we scroll down here, also, we do find this thing called Windows Credential Manager. Does not seem like anything much, but we'll be going through more of it in the dynamic and also in the advanced static analysis. And once again, once we scroll down, we can see that this program cannot be run in the DOS mode. So this means that the strings are starting to repeat again, and the same exact strings will be repeated as following below. So that's the end of BinText analysis of the strings for the malware. So that's about it on the basic static analysis. So if we go back straight to our sites, so just now in the tools used, we've managed to use WinMD5. We've also managed to use PEiD and PEview to uncover the details like the packer, and also whether the malware is packed or not packed, and whether when the portable executable or the malware is also compiled at like what time it is. Through PEview and through Dependency Walker, we've also managed to pick up several possible functionalities of LuckyCat. And lastly, in BinText, we can also see there are actually several URLs that the DLL is possibly trying to connect to through the WebSockets or the WebSocket a DLL. Yeah. So with that, that's it for the basic static analysis. Thank you for listening to this.
Okay, so for the basic dynamic analysis, this is usually carried out once the basic static analysis technique has been exhausted. So it requires the analyst to execute the malware and examine the system after the malware execution. It allows the analyst to observe the changes being made by the malware and is more efficient in determining the malware's functionality. So as the execution of the malware is required, we took a snapshot of the virtual machine running the FlareVM tools, and this snapshot included all the tools as well as the malware sample. This will allow the analyst, which is us, to actually roll back the virtual machines to reanalyze the malware when necessary. And the tools that will be used for this basic dynamic analysis will be the Process Explorer, Process Monitor, RegShot, ApateDNS, as well as NetCat. So this will assist us in capturing any modification or creation of the process or activities within the system.
Hello, my name is Sherlena, and today I'll be going through the static dynamic analysis for the LuckyCat malware. So firstly, when the LuckyCat malware is downloaded and unzipped, malware.exe file is the malware with a .exe file extension is seen. So on running this malware.exe, it states that the app cannot be run, and to check with the software publisher to find the version for the PC. So after putting it through the PEview and analyzing the image file headers, we can identify that this malware file is not a .exe, instead is a .dll file. As such, the file extension was changed. And in order for a .dll file to run, it requires the run32dll.exe file, which is provided within the Windows system, as well as the export function callable by the malware. So using the Dependency Walker tool, we identify the getObjectCount function, and we use it to run the malware. So before we perform the static dynamic analysis, we prepare the tools. So we will be running the tools to capture the processors, followed by the tools to capture the network activity, and lastly the tools to capture any registry activities that takes place by the malware. So in order to capture any network activity within the system, the NetCat running on ports 80, 110, as well as 443 was configured. So other than this ports being configured, the ApateDNS was also set up with the DNS reply IP of 127.0.0.1, which is the local host, which is a loopback address. So after which the server is started, and the run dll32.exe command was run with the malware.dll file and the getObjectCount, which is the function call for the malware.dll file. So upon execution of the malware, we are able to see that there is some network activity being sent to a specific domain. So we are also able to see that on port 110 there was a connection that was established, and there was no connection that was established on port 443. So this information sent on port 110 was encrypted, and doing a little bit of research on port 110. Port 110 is port 3. It's the port for port 3, and port 3 is usually used for a mail server. So it's likely that the malware is sending a mail with some information towards this specific domain. So upon searching up this domain within the VirusTotal tool, we are able to see that 6 vendors have actually flagged this domain as malicious, and within the relations tab, we are able to see that there were 3 communicating files that were found, and one of it, and this file being the hash of the SHA1 hash of the malware.dll file that we are using. So after capturing the network activity, we will next proceed to analyze the processes created by the malware. So to monitor these processes created by the malware, the Process Explorer tool as well as the Process Monitor tool is used. So the malware is ran, and after the malware has been ran, looking at the Process Explorer, we try to identify any new processes that was created. In this case, the processor that was created was the run.dll32.exe, and to confirm that the malware is running, when we'll view the lower pane, and within the DLLs, we should be able to see a malware.dll. So this malware.dll is being concealed as the Windows Credential Manager under its description. So looking at the properties of this malware.dll, we are able to notice that there are strings. So there are strings between the image and the memory. So to check and to view if there is any changes made within the strings are copied out. And a text comparer, online text comparer is used. So copying out the information that was being saved of the strings. We input the image on one side and the memory on the other side. So after which we click the compare button and review the comparison between the two files. So we're able to see that some of the strings, some strings has been added, and some of the strings has been appended. So if you were to scroll all the way to the bottom of the file, we're able to see that some uh, Windows Windows path was picked up of the run.dll32, and also the file description of Windows Credential Manager was picked up. So they also picked up the original file name, which was Credentials.dll, which is one of the file names this malware goes by. So going back to Process Explorer, we also are able to take a look at any mutexes created by the malware. In this case, some mutex may include the session 1 base name objects, will staging 02, and dbwin mutex. So if we were to copy this mutex names, we would search it up in the strings that was in the memory as well as the image of the malware. So if these names are actually found within the memory file or the image files, it means that this mutex belongs to the malware. So we can actually see that neither of the mutex can be found. So this could mean that the mutex that is created could have possibly not been by the malware, but the other DLLs that are running within the system. So moving on to process monitor. So we first create a filter. So using the filter, we are going to filter by the process ID, and the process ID of the run.dll32 is 1776. So after that, we will add the filter, and we'll filter the process monitor by the process ID of 1776, which is run.dll32.exe. So after we have filtered it by the run.dll32.exe, we will actually scroll down to look for the malware.dll file. So once you actually see the malware.dll file, we are able to see that some creation of file mapping, some registry operations are actually taking place. So this could mean that the malware may be trying to modify some things within the registry, and is also creating files and file mappings. So another thing that is interesting done by the malware will be to query basic information. So we are able to see that they are attempting to query some basic information as well as querying of some security files. So this could mean that the malware.dll is attempting to query for some information for them to actually capture, and using the POP3 protocol that we found from the network operation. So, this may be the information being sent over by the malware. So after after we have analyzed the processes created, so we'll be looking at the registry operations next. So to analyze the registry operations done by the malware, the RegShot tool is used. So the RegShot tool is configured to actually scan the directory of the entire C drive to ensure that any files that is created or any registry operations done by the malware is captured, after which the first shot is taken. So this first shot will capture the state of all the processes and any running processes and the information will be used to compare with the second registry shot, and the differences will be outputted. So the first shot is usually captured before the malware is executed, and the second is around a minute or two after the malware has executed. So after the first shot has been taken, the information about the device will be outputted and the malware is executed. So after this malware has been executed, we'll wait around 1 to 2 minutes before we capture the second shot. So once about 1 to 2 minutes has gone over, we'll take our second shot. So once the second registry shot has been taken, again the output values are shown, and after which we press the compare and output. So this will output all the information of the changes that was found to be have been made by the entire system, and output it into a text document. So once the output is done, we can actually analyze the malware. So over here, we see that there are some keys that has been added and deleted, and within the values modified, there is some audio journal render software. So this could possibly be something that the malware may be trying to disguise as also. So and if we were to scroll further down, we are able to see that there is some text which seems to be encrypted. So if we were to copy this out and we were to type it in, so looking at this, it looks like a rotation cipher. So we can actually see that rot 13, it will give us a UEME CTL session. So we can also scroll down further and we'll see more like pzq.rkr. So if we were to copy this and we were to input this, is the command prompt. And another drive which seems a little suspicious. So it's actually the RegShot tool. So other than that, it seems that not many other registry operations or any file operations were being conducted. So that is all for the basic dynamic analysis.
So next up, we have the advanced static analysis. So this method of analysis is used when basic static and dynamic analysis, basic dynamic analysis is exhausted. So this analysis method is understanding the malware's code on a assembly code level. So it's closer towards the code that is used to instruct the machines and our computers on what instruction needs to be done. So this analysis actually provides more in-depth analysis as compared to the basic static and basic dynamic analysis. However, there is a prerequisite of having the need of having a strong background in assembly code to understand the code that the malware author has coded out. Unlike dynamic analysis, to advanced static analysis does not require any previous like setup or any sort of snapshot to take of the VM, as the program is not run. Firstly, we are analyzing the malware by using the disassemblers and decompiler function of the tools that were mentioned previously, and these tools actually allow the malware analyst to read the assembly code that is stored within the malware's code, and also using the decompiler function of certain tools that was previously mentioned, we are also able to generate pseudocode so that the assembly code is slightly more human readable and also understandable, for easier for the malware analyst to understand the code and its function. So an advanced static analysis also enables the malware analysts to identify the general behaviors of the malware and gain a deeper understanding of the malware's intentions. So as previously mentioned, the advanced static analysis tools are IDA-free and also Cutter, which each have their own benefits and functions that were used within this project. So for IDA-free, it was mainly for viewing the assembly code and using the graph view of IDA-free so that we can understand the program flow. And for Cutter, it was used to decompile the assembly code so that certain assembly code that was more obfuscated and also a bit more hard to understand, Cutter was able to translate all these assembly code into a higher level programming language code so that it was easier for the analyst to analyze the code and understand the malware's functions. Hi everyone, so today we'll be talking about the advanced static analysis of the malware LuckyCat. So advanced static analysis is one of the 4 analysis methods that are used when trying to analyze malware. And today for advanced static analysis, what this method of analysis does is that it involves examining the source code of the malware. So this means that the goal of this method of analysis is to identify the malware's program's functions and features, and this is all done by examining the assembly code of the malware. So unlike dynamic analysis, there's also no setup required. As for static analysis, we're simply just looking at the assembly code of the malicious program. However, for dynamic analysis, they are running the malware on the virtual machine. So in static analysis, there's actually no damage, or we do not see what result the malware has done on the virtual machine. That's about it for static analysis. So firstly, for static analysis, just like to mention that we'll be using 2 tools today for static analysis. Firstly, it's IDA-free, and the second one is Cutter. So without further ado, let's go to our VM. So as usual, we open up our FlareVM, and the first tool that we'll be exploring today would be the IDA-free. So under the tools, we go to disassemblers and we see IDA-free. So just click OK. And because I've previously already loaded the disassembly file in, so I'll just be clicking on the LuckyCat previous file that I've actually created. So over here, IDA loads the thing, and you can see instantly you're brought into the IDA interface. So as you can see here, you're brought to the entry point of the DLL, which is the start of the DLL. So, all right. First, when we get into IDA, I think that's good to mention that there are 2 kinds of views here. So firstly is the graph view, so it'll show how the code blocks and the program flow goes about with all these tiny little arrows that I'm hovering over. And on the left side, there's also a graph overview, so it shows you a good view of what code blocks are in this subroutine. So firstly, what I would like to do is usually we'll go to the export function first of the DLL, as this is the start point of calling upon the DLL to run. So for LuckyCat Malware, the export function is actually get object count. So I just click on get object count here for the function. You can see that I've been shown what the program flow is. So over here we have get object count, and we see a bunch of variables that are assigned. However, we're just gonna move on from this, and as you can see, straight from the start here, you can see that there are three variables, three parameters being pushed into this function here called get module file name w. And after that, we can also see a character lower w function. So I think if this pad, along with all these two pieces of information, we see a bunch of strings here spelling out run dl32.ex. So this might be referencing to the run dll32.exe, which is the executable that is used to run any sort of DLL. And perhaps over here, with if we look at the file name and character lower, and then it's doing this, and then you can see if you scroll down further, we see a string. We're seeing a search here and the first. So with all this information, you can guess that the first what this bunch of assembly code is doing is that it's checking whether the run dll32.exe file is being used to run the LuckyCat DLL. Yep. So after that, we see we jump over to the next code block here. There is a call to a subroutine over here. So let's go to the subroutine 12E7 and just double clicking on it. So right now you can see that we're in the subroutine of 12E7. And at the start, there's a lot of variables once again, so we'll just ignore them for the time being. And then you can see a call to a local probe, which is actually a function that helps to ensure that things are running smoothly, because what it does is that it checks whether the destination location of the destination register, which is the destination location of where the next variable that might be stored in is free. So it checks whether that register is free for and has enough space to store the value that we want to put into it. So yeah, and if we scroll down here, we see a bunch of junk text and strings that don't really make a lot of sense. Yeah, so maybe I'll highlight this call, as we are quite interested in any sort of subroutines that may be popping up. So we jump over to the next code block. There's also not really much that we can see. We see some substitution, subtraction, comparison, division, and also some XOR. So there's some sort of comparison over there, but no worries, as we move on to the next code block. So the next code block here is quite interesting. The first command here is a load effective address that's talking, and there's a comment next to it saying LP subkey. So it seems that there's a subkey that's assigned into the ECX register, and after that we see a call to a subroutine 10C6. So perhaps we'll just follow this and we click into the 10C6 subroutine. So ignoring the usual attributes at the top, we scroll down and we see there is a string length w. So it seems that it's checking for the length of the string of perhaps LP string. And if we scroll down, there is see another subroutine 5730. So 5730 is actually a very special subroutine. We'll be seeing this quite often throughout the entire DLL. So if you just click on it, just like to show you quickly that there's actually quite a few if-else code blocks here. If you can see that it goes, it's quite conditional. It seems like it's checking into several of the registers that we're seeing, like ECX, EDI, and yeah, essentially an EAX too. So it sees that there's quite a few of if-else code blocks that seems to be checking for something. So to go back, I'm gonna press on the arrow here at the top left-hand corner. So now we're back into the 10C6 subroutine. So seems that the value that is returned from the subroutine is then actually possibly used in the upcoming and following commands and instructions. So we'll just be moving on. So you can see over here that the strings here actually spell default string. And you can see that is also copied like letter by letter, so character by character. So this is actually one method of defense of that the malware authors probably have set in place on this malware is so that there's a string by string copy rather than a full sorry, apologies, is a character by character copies, and instead of having a full string copy over there, it says the malware has opted out to copy string character by character. So this makes it harder for analysis to occur if there were no comments at the side here. So moving on, you also see at the bottom, you see reg open key here. Reg open key is a registry. It's a function to open registry keys, and perhaps this default string has some use to along with this registry. So I think if I'm not wrong, also this default string is also a placeholder for a registry key, as usually registry keys can be assigned to a variable that has a name or no has a key name or has no key names. So this default string here might be a registry key placeholder. Then as we move on, we can see even more parameters push and more registry functions. Registry query the value, and then it creates the key, and then after that we go down more. There's a code create GUID. So code create GUID, as I think I previously mentioned in the basic static analysis, what it does is that it creates a globally unique identifier. So what this does is that it creates a unique identifier within the target computer that is easily accessible and can be used to re-reference the same object again. So in reference with that, there's also several registry functions nearby this function. So we can probably tell that this ID is actually created specifically for the keys that was perhaps created above. So if we scroll down, there are several also more calls here and there to subroutines that don't really seem to be doing much. So you can see over here that it does a bit more comparing, but apart from that, it's also not a lot of functions. So we go back to the 10C6 subroutine and continue. And as we go down, we see more registry functions of setting the value. So it gives the idea that LuckyCat has registry viewing and also editing functions as seen above and over here. And lastly, it closes the registry key so that the registry values can be also saved, and then it ends. So for this subroutine, that's about it. So we jump back into the previous subroutine that we saw. So it's the 127 E7 over here, as you can see. And we were previously right after a right. So we've actually gone through the 1036, and we talked briefly about 5730 subroutine just now, and we talked about the default strings and some other subroutines here that are not exactly super important. There's once again more registry editing and viewing functions that you can see. So you can definitely confirm that LuckyCat has registry viewing and modifying sort of functions. And you can see here that there are also strings that are being assigned to the EAX register, and after that there's a string copy. And apart from that, there's also more strings copying. So, and after this, we do see a offset of possible URL over here. So you can see that the URLs leading to Dalai Lama Trust India.ddns.net and at port 110. And moving on, you can see that there's also a few commands here, move sd, rep, move sw. What it does is that this copies the value at ESI and then saves it in the EDI register. So it's seen that the malware is trying to copy several URL locations and perhaps saving it into the memory for further use later. So store SW also does this pretty much around the same of copying and saving these values into another register. So the same is also done over here. You can see that this IP address 115.126.6.16 is also being stored. And after that, we move on. So we see a few more subroutines, 5730 900B 184, and you can see when you enter them, that's not really a lot, and it just checks through some stuff here and there. But once again, it's not as super important. So we go on to the next code block, and we can see even more functions, calls to 5730, and we see a function that goes for FD6. So over here, we can see, once again, lots of if-else statements and code blocks, and we also see like a lot of conditional checking. So perhaps these functions are actually checking for a certain condition or value of a register. Okay, so if we scroll down even more, we'll see like 1026, which also doesn't really lead much to anywhere. And it calls other subfunctions, subroutines that possibly help the malware to run. So also over here, you can see there's also more checking functions. And there's also a string length comparison before we go downwards. So this part, once again, we see 5730 subroutine, and we can just simply ignore it. And what's interesting within this code block is that we see this DLL start connect to WSD. So what this actually could reference to is that the DLL is trying to connect to a WebSocket or window web server, so web service. So could mean a lot of things, but essentially it's just trying to connect to perhaps a remote network location. So this might link to the information we saw above, where there were 3 URLs that were leading to Dalai Lama India Trust .ddns, which is like a domain, remote domain. So further, if we move down, we see 1082 function subroutine, nothing much. We see output debug string A. So what this does is that it prints out the debug string or the results of a certain let's say a function. And perhaps the LuckyCat might be saving this too, because any sort of indication that the malware is running would definitely alert some people to the fact that LuckyCat is running. So perhaps this is being used to is being saved here and also suppress its values. It's also possibly used in the checking of the code functions, because as you can see above, there was these 2 subroutines here, 5730 and 1082, that were possibly checking the checking for certain conditions to be met. So perhaps this output debug string was also debugging out, like printing out any sort of a result from these 2 subroutines. So if we follow on, we see create event W. So create event W is just creating a synchronizable process or thread between multiple processors or like objects or processors on the victim's computer. So yeah, there's not a lot of things. So you can just simply move on. And as previously mentioned, a lookup just ensures that the malware can run smoothly. So if we go to this one here, 1FDF of the subroutine, we can just scroll down and we see 13F70. So as you can see, there's even more extensive tracks, and if you can see on the graph overview, it's actually a very extensive, and you can see that there's also switch cases here. There are 4 switch cases to a jump table, and there's even more switch cases at the bottom. So it seems that like it's trying to match whether the input of this subroutine is actually matching a certain function. So it's definitely something of note. And as we go down, we see 2495. So if you click onto this subroutine, this where things get a bit more interesting. We see some string copies, and so we see more like checking of the thing. So we see 13F70. We see SD over here, percentage SD, which is something similar to like a printf function, but the formatting that is used for a printf function. So we can see here that probably something is being printed out. So if we go under this, that also leads to more subroutines that help the malware to run. So if we enter the 2E78 subroutine, we can see here that actually now we see a socket, and what this means is that the socket is a function that creates a connection between the victim's computer, which is this computer, and a remote location that is specified. So if we scroll down, you can see that there's probably some checks on the strings, and after some checking, we can see that there's a get address info w, which is a function that is used to resolve the URL link translation into something that the computer understands. And the same goes for the free address info w and htrans. It helps in network remote network location resolution, so that it's from human readable to something the computer understands. And we can see that the socket is actually connected. And over here, we can see that the socket options has also been configured several times. And then there's a closed socket to signal the termination of the connection. So that's about it for this subroutine. So now we go back to the previous subroutine we were referenced to, and there are more string copies here and there, but essentially the rest are quite are mostly just checks, or just see closing the socket and just checking whether things are okay. So yeah, and then if you can see here, there's also a few more subroutines that are not really that interesting also. Then there's a set event here to set a perhaps a process or task for a set number of milliseconds with a certain handle, so that you can reference to it. And in the next subroutine, if we go back to the main subroutine of the 12E7, you can see that this is closing the handle that was previously created in the previous subroutine at the bottom here. So if we go down to one of the last few code blocks, we see that there's a sleep function here. So this can be used by the LuckyCat to maintain persistence on a device, so that the malware will just simply pause its execution and stop running. So any sort of like anti malware or any sort of malware scanners on the target computer actually will be unable to detect that LuckyCat is running because it's sleeping. So in this suspended state can help. This suspended state can definitely help LuckyCat. So can see that the malware authors have also included this function so that LuckyCat can continue maintaining and evade detection within the target's computer. So after that, that's about it. We finish at this subroutine, and that's pretty much it for IDA fruit. So next we'll be using our next tool to explore more about so we'll be using Cutter to explore more about the different code code blocks like the if else and the all the switch cases that we saw. So I've also previously opened the LuckyCat file inside Cutter, so I'll just open it here. And I set the thing to auto. So Malicious will let it run. It's usually pretty fast, takes less than 10 seconds usually. So yeah, you can see that it took about 8 seconds. So once you get in, you can see that this is the main startup, and you can see the functions here. So one function that we're definitely extremely interested to know more about is the check case that we keep seeing within IDA, which is the 5730 subroutine. So if you can see on the left side here, the functions are listed, and you can see here 5730. So if I double click on this, it will start loading the function. As you can see now, it is showing the decompiler. This is the decompiler mode. So if I switch over to the graph mode, it'll tell me like the exact graphical details. And you can see that the else, if conditional blocks are all here, and it's quite a mess. So we'll use the decompiler to make it so that the code is translated into like a high level programming language code. And so you can see here that the if here is asking for several conditions. So like the ECX is equals to 0, or is the ECX less than or equal to a hex number. So this goes on, and this actually does a few redirections to other labels within the code. So if you scroll down, there's more labels that we've seen, label 3, where you go to reference to another label here and there. And I think one important thing that we should note of is that most of the labels actually end up either with a incremental and decremental of EDI and ECX, and also if not, it will be returning the EAX function with this commentary lines before it completes the this function. So you can see here there's a incremental, and there's also the ending where it returns the thing, and a few redirections here and there. So it seems that like clearly that it's trying to, this functions and similar other functions where we saw the switch cases and the if else, they're actually trying to check for certain conditions. And if let's say we tie this knowledge in with what we've learned from the basic static and also basic dynamic, we can figure out that LuckyCat is on this, is probably it's a high probability that LuckyCat is a spyware. And this can be seen from like the keylogger functions that we found in basic static analysis. And also previously we saw like several registry function changes in IDA, and also several connections to, let's say, a remote network location. So it's trying to connect to those locations at previously mentioned 110 POP3, which is the POP3 command protocol, and also at 443, which is a HTTPS. So I think it's a good point to note that perhaps due to this knowledge that the LuckyCat is a highly probably a spyware, we can note that perhaps the malware authors are also using LuckyCat to further exfiltrate any sort of like data on the target computer. So there must be some sort of commands that send from the malware authors to the malware itself to execute on this victim's computer. So it seems that perhaps what's happening is that these functions that we've previously seen that have all these if else code blocks and switch cases are trying to check through the commands and see which commands that the malware author has sent over, and also to see whether the and try to set the registers so that they are ready for the command to be executed. Yeah. So with that, that's it for the static analysis. So once again, just a quick recap of what we did today. We did static analysis on LuckyCat using IDA-free and Cutter, and we've uncovered that LuckyCat indeed has registry manipulation features, and also it's also able to connect to a remote network location using the socket that we have found. And apart from that, we've also seen that there are defensive measures that are taken by the malware author, like in terms of evading detection using the sleep function, and also evading analysis. So, like for example, the default string that we saw just now, that was instead copying character by character instead of string by string. So this shows that LuckyCat is indeed quite complex and comprehensive malware that is quite interesting to be analyzed. Thank you for listening for today, and that's it for advanced static analysis.
So for advanced dynamic analysis, the analyzing of the malware will be done through the debugging as well as reading of assembly code. So this will enable the malware analyst to identify the complete process of the malware's operation and better analyze the malware. It also provides a better understanding of the malware's intention compared to the basic static as well as the basic dynamic analysis. And the tool that is being used for advanced dynamic analysis will be X32DBG, which will assist in the debugging, the viewing, and will be used for helping to break points and to analyze the code slowly. So this operation and any operations occurring to the system during the execution of the malware will also be seen using the debugger.
Hello, my name is Sherlena, and I'll be explaining how to conduct the advanced dynamic analysis on the LuckyCat malware. So the LuckyCat malware, as we know from performing these basic static analysis, that this malware file is a data link library file or a DLL file. As such, in order to run this DLL file within the debugger, it will require the run dll32.exe. So before we start, right, the debugger that we'll be using is the X32DBG. So the X32DBG is the 32-bit version. Is made for 32-bit malwares, whereas the X64DBG is made for the 64-bit malwares. So firstly, in order to run this file, we will be opening up the run dll32.exe file. So this run dll32.exe file can be found within the C drive, Windows, syswall64, and you will be able to find the run dll32.exe file. So this syswall64 is the Windows system for the 32-bit executable files. So after which it will be open. And once we have opened it, we're gonna set our options. So under options and preferences, we are gonna select for the for it to break on the DLL entry. So this will be important as we will be able to identify when the DLL has been loaded and has entered. So another thing that we'll be doing will be to change the command line. So we're gonna add a space, and we're gonna add the file path of this of the malware.dll file. So I'm gonna place it in quotations. And after which we're gonna enter the export function of this malware.dll, which is get object current. So after which we're gonna save it, and we are gonna restart this debugger. So once we have restarted this debugger, we'll see that we'll have loaded into the module ntdll.dll. So we are just going to continue running it until we run into the malware.dll file. So once we have noticed that the module name has reached the malware.dll file, we are going to go towards the symbols panel and we're going to look for the module of malware.dll. After which we'll notice that our exports and imports are all here. As such, we're gonna click onto the address of the export function getObjectCount, and we are gonna set a breakpoint there. So we're gonna do the same, setting the breakpoints for the registry operations, such as the setting of registry values. We are gonna do the registry create key, registry open key, as well as the registry querying of the values. So other than breakpointing the registry operations, we're also gonna breakpoint the send function. So after we have breakpoint these few functions, we're gonna continue to run our we're gonna continue to run this malware. And you can see that we have hit the get object count. So before we actually start to debug this get object count, we're gonna set up our network operation tool. So we'll be using ApateDNS, and we will also be using the command prompt to run the NetCat command. So the NetCat command will be set up to listen to port 110, as we know that there is some operations made to connect towards port 110. And for the ApateDNS, we're gonna set the loopback address of 127.0.0.1 as the loopback address to listen to all the DNS being made up of the system. So once we have set that up, we will continue to execute the malware. And we will see that it will start off the registry operations. So we actually noticed that from the operations before, which is to open a registry key, we noticed that there is a path that is actually stated, and that within this pane of all the registry information, we also see that there was an error. As such, right, we will be using the regedit tool, the registry editor tool, and we are going to add this path so that the malware will be able to detect it. So we will just add a new key with the key of resources. And we'll leave the value as defaulted. So once we have created this key, we will just rerun this debugger again. So back to the point of where we see where we breakpoint to this registry open key. If we were to actually run it, it shows that the status was successful. So so we'll just continue running this. And we will see that registry value of this value seems to be set. So we're just gonna copy down this value and we're gonna put it into a notepad. So after getting this value, we're just gonna continue debugging. So it's seen that the registry value is actually being queried. And after which we have reached the send function. So to get the value of what is being sent, I will just follow the EDI registry. And we can actually see that a bunch of gibberish was printed out. So I'm just gonna copy all this gibberish out. And I'm gonna paste it into CyberChef. So I'm just gonna extract the text. And I'm gonna push this information that I found. So after which we'll take a look at what happens. So we will just perform a step. So we'll just perform step overs until we hit a return function to try to find any encryption keys that was being used to encrypt this information being sent. Okay, so this seems to be the point of when the function was ran before it actually called the send. So we're just gonna breakpoint this area and we're just gonna scroll up and read some of the assembly code. So we can actually see that the XOR operation is being performed quite frequently. And it shows that one of the functions actually shows that the XOR function with a specific address was actually XOR with the value of F5. So let us return back to where the value that we found here. And since we know it's an XOR operation that was performed, so we're gonna key in the key of F5. So when we actually decrypt it, we are able to see that this value here is similar to the value that we previously found. So it is actually the same value. And if we were to look at the information being sent over, it seems that it's sending over this work group and the desktop. So this is likely the settings of the current user that I'm using. So if we actually go to system and info, we should be able to find out that the desktop name, the device name is matching, and also the work group of this user, which is work group. So knowing this information, we still have this string that we have yet to find out. Knowing that they were trying to perform a registry operation, so we're just gonna take a look at the this web resources where they were trying to access, and we're gonna refresh this key. And we are actually able to see that a new string has been created. And if you were to click onto this string and view the binary data, we will actually notice that this string is the same as the one written in this that we have found. So based on this, right, it seems that this malware is attempting to retrieve the credentials from of the user from the device, and giving it a unique identification number to identify it within the list of within a list of the of machines that the attackers get a hold of. So this is most likely the a possible way that the malware actually uses to ensure that they do not reinfect the same device by being able to read the data and check if this folder has been created. And that is all for the analysis for the advanced dynamic analysis.
So for the conclusion and reflection of the LuckyCat malicious executable that our team has examined, so we have determined that LuckyCat is most likely a spyware, and it can monitor the user activity as well as as well as harvest data. So some data that this LuckyCat malicious executable actually harvested will be the name of the computer as well as the group that the computer is under, and by creating a unique identification number and storing it within the registry. So this poses a serious threat to the privacy and confidentiality, as well as the security of the infected devices, as well as its users, as this LuckyCat malicious executable also masquerades as a Windows credential manager. So for my reflection, I learned how to be patient and persistent as through the basic dynamic analysis, the tools like RegShot kept hanging, and every time we captured the registry, it always takes a really long time. So I also learned how to be persistent and to keep trying again whenever the NetCat and ApateDNS captures a lot of noise from the external services such as the Windows updating, Google Chrome updating, and this actually made it quite difficult to differentiate between the connections being made by the Windows machine as well as being made by the malware. From this real world analysis of the malware, I also, as it was the first time that I performed a advanced dynamic analysis using the X32DBG, I was slightly overwhelmed with by having to understand the assembly code of this malicious executable and the actions it was performing. So I managed to learn how to use the X32DBG symbols tab, and as well as some Google search helped me to learn how to debug this data link library file, and where I could breakpoint for the various functions in order to help me to read and understand the process of the malware slowly.
So for my reflection, I have several learning points to talk about today. So for my first point would be that I learned to be more meticulous. So during the project, I felt that I was rushing through on the advanced static analysis, as I felt that there was a lot of code to go through. However, while rushing through, I actually missed out on several subroutines that had quite important imports, and also because I rushed through, I was not very detailed in terms of finding certain subroutines that actually mattered to the malware, and ended up finding and getting lost in several other functions and features. But not all was in vain, as by getting lost within the code, I also managed to gain a familiarity with assembly code. So previously, I was not very strong in understanding assembly, and I had to be frank to have I had to be frank, and I didn't have a strong understanding of what assembly code could do. But through getting lost within the code, I was able to actually pick up new functions that were not commonly seen in our school's malware, like all those weekly labs that we do, or like when we do malware analysis within class practicals. So, for example, one of the new features and functions that I learned was SEH prolog, which means structured exception handling. So it's actually a very important function in a lot of executables, as it provides exception handling support for any sort of like executable. So that was definitely very new and fresh, because this is not commonly seen or taught in the classroom. Another thing about gaining familiarity with assembly was that I managed to find more and learn more about defensive measures that the malware authors use to make sure that their code is and like it is harder for code to be analyzed. So I think for this, I was quite lucky that I searched online and also had uh, some support from my teammate Sherlena on finding all these defensive measures within the malware's code. So third point on what I've learned is that I've learned how to use Ghidra, Cutter, and IDA within this project. So actually, two of the three tools were actually not touched before, which is Ghidra and Cutter, at least within the school syllabus. And for this project, I had to quickly pick up and learn the skills on how to use Ghidra and Cutter, so that it could help with my disassembly and also decompiling of the assembly code. However, unfortunately, as you can see on the right, the picture here is actually what the decompiler output for Ghidra, and it's actually not very human readable, which was the reason why I had to learn an additional tool, which was Cutter. And I found that Cutter was more effective than Ghidra, and therefore I used Cutter within the project. So and also, I had to solve the issue of not having enough context due to inability to run programs. So initially, I only wanted to do IDA free, and only use IDA free's functionalities of the graph overview and also the assembly code disassembler. But I felt that it was not enough, because I was unable to run the command or run the entire executable. So which means that I did not know what values that the registers or certain variables had. So I felt that most of the time when I was looking through the code, I did not know which program flow the code was actually taking. So I just looked through pretty much everything, which was quite time consuming. So out of all this, I think I've learned how to be more efficient in picking out important code, because after reading through quite a lot of assembly code, I think I'm able to now, through this project, I learned how to pick up which instructions are more important, and also are like they have higher potential of being indicators of what the malware actually uses. So lastly, I learned more about command and control servers. So because LuckyCat is a spyware, and after it obtains the data, it actually sends the data back through the POP3 protocol. So actually, it sends back to this command and control server, which I did not know was a thing until this project. So I think after knowing that that command and control servers exist, which is a server where the malware authors will actually obtain the stolen data of the computer, and then after that craft a meticulous and sophisticated attack crafted specially just for the victim computer. So I think after knowing command and control servers, I know more about how to secure and also understand the importance of security controls in like endpoint devices like our individual host computers. Yeah. So I think if these are all like my reflection points from this project, and with that, I'd like to thank you for listening in to our project explanation and also our videos so far. So thank you and have a nice day.